Okay, let's begin. So today I want to finish up work. Probably won't move on to the next topic. Probably won't flow very well. So we'll see. So we'll probably have a little fun with this while we're doing it. So we're going to look at the last problem type. We're going to look at pumping liquids. So here is going to be the main idea of the main equation. Of course, we're still going to start out with work equals force time, well, force dx, where a to b of f of x dx, where the f represents a force, and your dx represents the unit distance. But now, we are going to measure force in a particular way. We'll measure force in this way. We're going to think of force as a volume times a density. Now, normally we think of density in terms of mass, like grams per liter or something like that, but we're going to think of the density as a force in this case. So like pounds per liter. So it's the volume and times the density. So you know that actually density is just the amount of stuff per unit volume. So if I say density force, I'm talking about the amount of force per unit volume. So these guys will actually cancel out and you're left with force. So if you look at force in terms of units of force per volume and multiply that by volume, that's another way to get force. This is going to allow us to actually look at liquids in a very convenient way. And so it's convenient to look at work in pumping liquids as volume times density times, well, change in distance basically. The idea being we are going to find the cross-sectional volume of some liquid. And multiply it by its force density. So we have 5 problems on this. So what we're going to do is I'm going to do one, and then you guys are going to do the other 4. So, and because I think I should be extra nice today, I'm even going to do the hardest one. So problem 5, 6, 7, 8, and 9. I would say 7 is probably the hardest one to kind of figure out how to get it to work. So I'll probably do 7. It's a spherical tank. So we have a spherical tank, so 7. So we have a spherical tank. Its radius is 10 feet. It is filled with liquid of density 20 pounds per cubic foot. Okay, so every cubic foot of this liquid that the tank is filled with, it weighs 20 pounds. The tank has it says 5 meters there, but that should be 5 feet. There's a 5-foot spout at the top of the tank. So it says it's filled. So this tank is filled up to the top with liquid. And so now the question is, find the work needed to pump the liquid out the tank through the spout. That's it. So you have a tank filled with liquid that weighs 20 pounds every cubic foot. We want to pump this liquid out the tank. How much work would that require? Hence, how much fuel? If I have a fuel pump, how much energy do I need to supply that fuel pump? Is another way you can look at this question. So here's how we are going to do the answer. What you're going to do is you're going to take a small infinitesimal slice of the liquid, which here it's going to look like a small little disc. I'm going to find the work needed to pump that disc of liquid out the top, and pretty much I'm going to integrate to show what would happen if I had to move all these slices of liquid. So I need a way to talk about the volume of this thing that I just came up with, so that I can multiply by the density, which we're told is 20. So here's how we're going to do it. So one small little slice here is actually going to be a cylinder. Let's say, again, I base my origin at the bottom, so this is x equals 0. Let's say the height of the slice I'm talking about, that's at height x. The thickness of the slice is delta x. Then, of course, the distance it has to move to get out of the spout is going to be what? Well, I know this distance here is 5, and this distance here would be what?
20 minus x.
Because the whole thing, it's 10 radius, so the diameter is 20. Here's what I am going to do now, though. So I know if I call the radius of this thing r, the volume is going to be pi r squared delta x. Problem is, what is r? If I'm trying to set things up into x's, I need to figure out how I'm going to find that r. Here's one way we can set up. I'm going to pinpoint the center. The distance from the center point to the edge is going to be 10 because that's the radius. This distance here, the height that I am from the disk to the center, that is simply going to be 10 minus x because that's going to be the radius. That's this distance here. And so my r is going to be that distance there. And you'll notice that I just formed a right triangle. So, and this is kind of what you're going to do with all these problems. You're going to figure out how to use geometry with the shape that you're looking at to figure out whatever dimensions you need to figure out. So, what we have here is a right triangle. There's an r here, there's a 10 there, there's a 10 minus x here. Pythagoras' theorem tells us how to find r. It says 10 squared is going to be equal to 10 minus x squared plus r squared. In other words, my r squared is going to be equal to 10 squared minus 10 minus x squared. It's the difference of squares. That's 10 minus 10 plus x times 10 plus 10 minus x. So that's just x times 20 minus x. That's my r squared. So this means my volume is going to be pi times r squared, but my r squared is this guy, times delta x. Now I kind of breezed by that, but the creativity in this process actually happened all over here by me trying to figure out using the diagram to my advantage. Try to figure out how would I get that r. So a lot of times you might have processes that you can, previous theories that you can use to help you out here, like Pythagoras' theorem is always going to be one that you can check if you can get a right triangle in there, or maybe similar triangles would be some that you can check, things of that sort, right? You're going to use your knowledge of geometry. So pretty much doing that, I was able to figure out the volume in terms of the distance x, which is the height of the slice that I care about. So this means that the work to move this slice of liquid is going to be volume times density times distance. Because this volume times density is how I'm thinking of force. Work is force times distance. So the volume is going to be pi r squared delta x. The density, I was told, is 20 pounds per cubic foot. The distance that this slice has to move would be, of course, 20 minus x to get to the top, plus an additional 5. 20 minus x plus 5. In other words, I can write the work to move this one slice as 20 pi times 20x minus x squared times 25 minus x times delta x. And then what I can do is I can now integrate that to find the work needed to move all the slices. So pretty much that process gets repeated for this slice, and that slice, and that slice. X starting at from level 0, going all the way up to level 20. So that means the work is going to be the integral from 0 to 20 of 20 pi times 20x minus x squared times 25 minus x times delta x. And I want you to notice here, you always want to know how you are setting up the limits. Now the limits, so in Hooke's law, you know that the limits describe the distance you are from the natural length. When you're looking at pumping problems, and for pulling problems, the limits would represent the distance of the thing that the length of the thing that you're pulling up. Here the limits represent, it's going to sound weird to say this, but the length of the liquid you want to move. So here, I want to move all the liquid from level x equals 0, measured all the way up to level x equals 20. If the problem asks something like, what is the work needed to pump half the liquid out, then I would need from x equals 10 to x equals 20. So I'm looking at a length that will cover geometrically the part of the tank that I want to empty. So that's how the limits are going to be set up. So I want to pump all the liquid out, everything from level x equals 0 to level x equals 20. That's going to be the integral. And you put that in the oven, and out is going to come 400,000 pi foot-pounds. I mean, that, for the integrals we've been doing, that's just a little bit annoying to multiply out and integrate, but eventually you'll get to that, which is going to be nice. questions on the process? Yeah.
Why wouldn't the upper limit be 25 and trying to take it out?
Because X is measuring the liquid, and the liquid actually stops here. Right? The spout doesn't have liquid in it. Right? So the liquid is all of this. Liquid is filled from level 0 to level 20. So the limits must describe the amount of liquid that I want to move. Right. If the liquid was actually filled in the spout, what I would have to do is I would actually have to do a separate calculation for that liquid here, because its radius is going to be given different from this one. So, but that is not the case. It's just the tank that's filled. So I'm not really worried about the spout itself. I just want to move all X values from 0 to 20. Other questions? Yeah, so the main thing is this. Take a slice of the liquid that you want to move, just some typical slice. Figure out the volume times density times distance for that slice and integrate it to actually find the work needed. That's the basic idea. So, to me that is probably the hardest example, because actually coming up with this construction, I think it's not something that would be obvious to do to someone who hasn't seen this before. But the others are, I think, more obvious. So what we're going to do is we are going to get into 4 groups, and one group is going to work on each problem, and then we'll have a representative tell me how to do the problem. I think that will be fun. Yep, that sounds like a lot of fun. She's all into it. Okay, you guys over there. Okay, go ahead. Okay, so you guys can do problem 5, and then you guys can do problem 6. Whatever group is going to be here, and then, and you guys are doing 8, and you guys are doing. So, I mean, by the time we get to another test, I'd expect you to be able to finish a work problem in about 10 minutes, so I'll give you guys about 15. Since it's going to be your first time, and then we'll go through it together. Okay, problem 5. This group. So, problem 5. An inverted conical tank is filled with liquid. The density is 200 pounds per cubic foot. That's really heavy. The tank has a height of 12 feet. The radius at the top is 6 feet. Find the work needed to pump the liquid out the tank. The tank is filled with liquid. Okay. What do you guys do?
First draw the
You first draw. So I assume it looks like this.
Yeah.
Okay. And so
With
they told us.
a height of 12 and a radius of 6.
Okay. And this is in feet? Feet.
Yeah.
Okay. Alright, what now?
We drew a small section, like took a little sliver of it, and it's in the, yeah.
Okay. And what did it look like? That?
Yeah. And we called that radius R. And then the height from the bottom to that would be X.
Okay.
And then we did the delta X on this side. And then we set up 2 triangles.
Well, where's your origin? At the bottom?
Yeah.
This is x equals 0, and you're measuring the height of this x. Okay.
Yeah, and then we set up 2 triangles, one between like with the entire cone, so it has a height of 12. Yeah, 6.
Okay, so there's this big triangle here, height is 12, that is 6, okay?
And then another triangle with R, and then X is the height.
Okay.
So we did a so we set up a ratio, 6/12 or 1/2 is equal to r over x. And then solved r to be 1/2 x.
Okay.
So then we plugged in to find the volume. So that's equal to pi r squared delta x. And then for r plugged in, x over 2.
Okay.
And then the distance that it needs to travel is 12 minus x. So we found the work for for just that slice is the volume times 200, the density, times 12 minus x. And then the work total is the integral of that from 0 to 12.
Right, because it's filled, so it's the whole thing. So it's going to be 200 pi times 12 minus x times, so 2 squared x. And what did you ultimately get?
86,400 pi foot-pounds.
Yeah, that's what I thought. So I'm assuming everyone would know how to do that, so the result would be 86,400 pi, and this is foot-pounds. Very standard kind of problem. I believe your textbook even has an example similar to this one. It's the solution for 5. How about, this was problem 5 on the handout. Problem 6. Okay, volunteer. So, let's read it. Problem 6. A rectangular tank, length 10, width 5, height 5, is filled with water. Water has a density of 1,000 kilograms per meter cube. That's known. Find the work needed to pump the water out the top of the tank. Okay, so what do we do here?
So we drew the diagram lengthwise, so just a rectangular,
Where it looks like a what?
like,
So like a box.
I don't know.
Okay.
And then we determined the cross section, so we knew that we're just going to use delta x as the height. So
What? Where's the cross section?
So it's base times the length times the width is the cross section. So
Well, I mean,
yeah,
you want to draw it in, right? So
yeah,
it's gonna look like. It's gonna be like another rectangular slice, a very thin one.
yeah.
Okay.
And so from there, volume. You knew that volume equals length times width times height, and then we're just going to use height as 5 minus x. So we just did volume is equal to 50 times 5 minus x.
50. Where are we getting the 50?
Like 50 delta.
So the length
Yeah,
here
50 delta.
is 10. This here is 5. This here is 5.
Yeah.
Okay. So this times that. That's 50.
Yeah, and then it's delta x for the density.
Delta x. So that's your delta x. What you're going to want to make sure you like set up your origin.
Yeah.
X equals 0. This is at a height of x. The
And
distance
that's
left
5 minus x.
is 5 minus x. Okay.
And then from there, we set up our integral, so w is equal to the integral of 5 to 0, 50 times 1,000 times 5 minus x, delta x.
So this is the so the 50 delta x, which is the 50 dx, that's going to be the volume.
Yeah,
And it's 50 times 1,000 times
5 minus x.
the distance.
Yeah.
So that's volume times density times distance. Okay.
And then if you take out the 50 times, or the 50,000, so you get 50,000, if you solve it, it's 50,000, 5x minus x squared over 2.
Okay. So there's an issue here.
So
see what the issue is. I mean, the methodology is sound, but there's something you guys are forgetting. Yeah?
Is it the units for density?
Yeah? What's the issue?
Since it's in kg, since you used shouldn't it be in kg over m squared, s squared?
Well, that's what they put, it's in kg. Kg is a unit of mass, not force. For work, we need force. How do we get force if we have mass? Yeah?
Times 9.8.
Multiply by gravity, so there's a times 9.8. So you definitely have to pay attention to the units. So that's the correct setup. And so then you'd end up with 6, 1, 2, 5,000. And with those units, it would be the Newton meter. Or you can write it as the joule if you want. So be careful of that. That was the units might mess with you if you have the wrong ones. For work, you need force. You need force, and kilogram is not force. But other than that, the setup was good. Just don't forget that. Pay attention to the units. Let's see. 8. A right cylindrical tank has a radius of 3 meters and a height of 6 meters. It is filled with liquid weighing 10 pounds per cubic meter. Find the work needed to pump the top half of the liquid out the top of the tank. Okay? So what are we doing here?
Alright, so first we drew the cylinder.
So it's a right circular cylinder. So
Yeah.
that's kind of the picture here.
And then we labeled the height as 6 and the radius as 3. We noted that the density was 10 pounds per meter cubed.
That's already pounds, which means that's a force already.
Yeah.
Right? So we don't need to multiply by gravity or anything. Okay?
Alright, so now we did volume is equal to pi r squared times the height. And we got
Volume of what?
volume of the cylinder.
Should the whole thing?
No, should it just be half of it then? So would it be pi times 3 squared times 3? Or would it be?
No. What are we measuring the volume of?
We're finding the volume of the top half or the.
What are we finding the volume of? Huh?
The cross section.
The cross section. You have to put it in the cross section. So you have to consider there's a particular slice that you care about. And you have to set up that slice. So how would we set that up?
Alright, so would it be instead of 6 for the height, would it be 6 minus x? Or
Well, I mean, setting up means you have to throw in a coordinate system, you have to describe the thickness, you have to describe the radius, you have to describe all of that. So how would you do that?
we didn't do all that, so I'm not entirely sure.
Any other group can help them out? Want to take a shot at it? Benny?
Wouldn't the volume be pi, the radius stays constant throughout, so it would be 2 for radius and then delta h. And then
Right, the radius of this is always going to be 3. Right, because it's a right circular cylinder, so the radius isn't going to change. What's your h though?
delta h.
dx.
I mean, delta h.
Yeah, but where is the dx?
The height of the slice.
The height of the slice is dx.
Or d.
What's x?
Bottom. From
What do you mean?
height
From the
bottom
bottom
is
to
x
the
equals
slice?
0,
So we're going to set up x equals 0.
and then from 0 to delta x is x,
The distance to that slice is x.
and then from the top to delta x is 6 minus x.
So the idea is you have to do it in slices, right? That's the whole point of doing the integral. You're dissecting. It's like you're doing a Riemann sum. You're like slicing these little slices, and you use an integral to add them up, just like how when you were doing Riemann sums. So you need to come up with a slice. You need to figure out the volume of that slice, and you need to set up some kind of coordinate system by which you can label where the slice is located with a variable. So we use x typically. So that being the setup, what is the volume of the slice here?
Nine pi delta h.
Right.
Delta f.
9 pi delta x. Okay, and so now what?
So now we integrate. I think.
Well, we find the work for that slice, which is going to be
Volume times density times distance.
so the volume we just found, that is 9 pi delta x. Density, 10, and it's already in pounds, so we don't have to worry about changing units. Distance,
6 minus x.
that's the distance it has to travel, 6 minus x. And so now we can do the total work. Here's where we throw in the integral. That delta x is going to become your dx because we're looking at this as a Riemann sum. And so it's going to be not 90 pi, the 9 pi times the 10 times the 6 minus x. What are the limits?
Should be P to 6.
Huh?
P to 6.
Right, so work needed to pump the top half of the liquid. So we're pretending that we are starting at here, like halfway up, which is 3. So it starts from 3, and we want to pump all the way up to 6. So that would be the correct integral. And that, put it in the oven, bing, 405 pi meter pounds, or pound meters. Okay. Problema 9. Problema 9. It's in Spanish and German. Okay. So, problem 9. A 10-foot long tank with height of 4 feet has a vertical cross section given by y equals x squared. It is filled to a height of 3 feet with liquid having density 30 pounds per cubic foot. Set up an integral to compute the work necessary to pump the liquid over the top of the tank. Okay, what's our setup here?
Alright, so first draw the diagram of the tank.
Yes.
It's going to look kind of like a semi-cylinder running on its side. Yeah. That is beautiful.
That looks better than that.
Yeah, that would make it not easier too. Alright, so now you need to define.
Secret to multi is knowing how to sketch things really well.
So if you don't, you will fail.
Your life is going to be a lot harder, let's put it that way. Yeah, when you're working in 3D, being able to, visualization is going to be very important because you need to know where things are located in relation to other things. Is this on top of that thing or to the left of this thing? Yeah, so, yeah, okay, so now what?
Now kind of define a slice. So if you could draw a rectangular slice. across
Right,
it.
it'll look like a rectangle here.
Yeah. So then therefore the volume of a rectangle is length times width times height.
Okay, length,
Length is going to be 10.
and we know the width of the top.
It's 16, I think. X squared. That's 4 feet.
How do we know? Because we know that the height is 4. So the height is 4. And pretty much if we think of that as the cross section of x squared, I mean, this was the game changer, right? What made it become more obvious is that you imagine that the xy plane is just along one of the faces here. So that being said, we know that when we obtain a height of y equals 4, the x would have to be what?
The width would be radical y, 2 rad y. So x is rad y.
So x is the radical of 4.
So then,
So this distance here would be radical 4, which is 2. That distance here would be radical 4, which is 2. So the whole distance across is actually 4, versus the whole distance across here is 2 radical y. And we're assuming then that this is your delta y, and of course the bottom is where y equals 0, y is the height, and to go up here,
4 minus y.
4 minus y.
Alright, so you have your length times width times height.
Right, and that's because we know that this is y equals x squared, but measuring along here, how do you think of that? Why did you measure that in y's instead of x's? Surprisingly, to be the question.
Because it's going up, it's easier. Because they gave you the function already.
Yeah, because they give you the function on y, but why wouldn't you describe this length in terms of x? How do you know that's not x squared?
X squared is the height part.
Is the height. So that's just you knowing about function, right? When you say f of x equals x squared, basically what that is telling you is when you plug in an x, the height is x squared, right? So the x squared is actually measuring that length, not that length. So to find that length is you measure the y. Okay. So that's how we know that that had to be measured in y's, and here we're measuring things vertically, so we're using y's, delta y's, all that stuff, which falls in line with the coordinate system. Okay, so now that we have that set up, how are we going to actually get to it?
So write out the volume is equal to the length times width times height. And that means it is equal to 10 times 2 rad y times dy, or delta y. And then the work of the slice is going to be equal to the volume times the density times the distance.
Volume times the density,
It's 30 pounds.
30 pounds. And that's already given in pounds, so we don't need to multiply by gravity or anything to change the units.
And distance is going to be 4 minus y.
4 minus y. And so, the total work is going to be
The integral of that from 0 to 3.
0 to 3,
Yeah.
because we were told that it is filled to a height of 3. So the liquid is starting from the bottom, now it's here, at 3, out of a length of 4. We don't care about the height of the tank, we care about the length of the liquid that we want to move, and it goes all the way from y equals 0 to y equals 3. And then we're going to put all that down where the delta y becomes the dy in the Riemann sum. And so that's going to be 20 times 30, that's 600 radical y times 4 minus y.
You heard about the two.
The what?
Times
2 is included.
2 root y.
You will flip in?
It's included. I took the 2 times the 10, which is 20, times the 30, which is 600. And so, yeah. And of course, that 3 to the y to the half multiply out, you can use the power rule. And ultimately, you would get, I believe, 2640 radical 3 foot-pounds.
So the height is 4.
And that's work. Did lots of examples. And now, hopefully, I want you guys to appreciate that technically the way we set things up, it's different compared from Hooke's law to pulling problems to pumping problems. Make sure you look over the strategies for each of those, because I can throw in a random work problem for any one of these sections on a quiz or a test. So, quiz next week is going to cover work, it'll cover arc length, and it will cover hyperbolic functions. Okay.